Okay, I think we're finally working. Holy cow. That was painful. Hello, Stefan. Can you hear me okay? Let's see how much of a delay there is tonight. Okay, great. Sorry I'm a little late. The internet decided to just completely obliterate itself at 9:59 when I click start streaming. So I think we're up, and I actually switched to the backup YouTube ingestion server, and that seemed to fix it. So I don't know what the heck's going on. But anyway, we're up. Okay. So let me see if I can launch Fusion again. I just figured we haven't done one of these in a while, so let's do one. I had a little bit of time tonight. Not much. I've been crazy, crazy busy. That's the truth, Josh. I think even Fusion had some downtimes. Was it this week or maybe it was last week? I saw the thing go red. No, sorry, Stefan. No, I didn't plan on any probe stuff tonight. Um, but we can talk about the probe if you want. Hello, Jason. Yeah. Well, that's how it always works, Josh. That's why cloud services are so awesome, right? So let me get a couple of these parts opened up so that I'm not trying to open them and stream at the same time too much. Okay. So let me switch screens here. So, as if I didn't have enough to do, the mentor for the FIRST Robotics team that I help out here and there contacted me earlier, well, late last week, this week, whatever you want to call it, and they need some help machining some parts. So I guess they're going to do a summer build. And what they did was this last winter's project, they built a robot that can pick up gears and then shoot balls. And I guess what they're going to do is they're going to try to build another team's ball shooter. So these designs are actually from another team, and they're asking me to machine some of the core parts that are a little bit beyond their in-house capability. So the high school that they're at has basically a Bridgeport mill with a DRO and a small lathe. I don't know what window machine I recon. I don't know what the exact robot was. Um, so they have a small lathe. It probably swings maybe 6 or 8 inches over the bed, and I think it has like maybe a 16-inch bed on it. So not tiny, but not huge. So those are the two main tools that they have at their disposal. So trying to make a part like this on an all manual machine is definitely doable. However, it is not doable in the time frame that they need to do it in. So the drop dead date for all of these parts to be completed is August 15th, which is pretty aggressive considering you need to order material, you need to order tooling. I got to go through the parts and cam them all, and then actually get them run on the machine, and then pushed out. So it's a fairly aggressive schedule, and there's quite a few parts here. So hello, Z. I'll just say your first letter there. So a lot of these parts are very large flat stock parts. So I figured I had a little bit of time. I haven't live streamed in a while, and the live streams are nice. Everybody likes it. Yep, that's pretty much what I'm going to talk about. We can talk about anything you want, Stefan. So I haven't done a live stream in a while, so I figured, this would be a good topic to do a live stream on, and then we can also diverge into other stuff because I haven't done a live stream in a while. I've just been hammered busy between my day job, working on the machine. The probe took way longer to get installed than I thought it would, just because I've had so much stuff to do. I've had tons of family and personal stuff to do over the summer. So, here we are. Yeah, so the way that so work holding, in my opinion, is a mythical creature. And what I have learned is that if your primary background has been in manual machining, you look at work holding one way. And I feel if your primary background is in CNC machining, you take a different approach to work holding. And then even between those two basic backgrounds, everybody does it a little differently. So that's why I thought this would be a good subject to talk about. We got a pretty good audience here of some pretty experienced machinists. So the way that I was going to hold this down, and this part has to stay fairly flat because what this piece is actually a very large bearing race. So they've got this part here. They're going to put 3/16 nylon balls in here, and then they've got this piece here, which is going to be the mating piece to it, and it's got a collar on it, and then the collar bolts into these holes here, and then that kind of holds the assembly together. So both this part and this part need to stay reasonably flat. I mean, it's a high school robot. It doesn't have to be flat within tenths, but it needs to stay reasonably flat. So the biggest problem you have now, this part is it's 14 inches this way, and it's 8 inches in Y. So 14 inches in X, 8 inches in Y. It's a fairly sizable part. So to get this thing to stay flat during machining is going to be a little challenging. So I think what I'm going to do, one, is I'm going to start with, it's 3/8 of an inch thick. So the thickness on it's 3/8, 0.3. That's about 10 millimeters ish for metric folks. So I think what I'm going to do is I'm going to use an oversized stock, and I'm going to clamp the four corners. Okay. Now the problem with that is, anytime you clamp the four corners, typically it's going to push up in the center of the plate when you clamp the corners. So then I'm going to also, drill a hole here in the center and then put a center hole down. And I think that should keep it fairly flat. Now, the other thing that I found is if you get extruded stock versus plate stock, extruded bar stock is almost always warped. I have not received a piece of extruded bar stock that doesn't have at least 20 or 30 thou of warpage in it. Plate stock I found you can get fairly flat. So the other thing that I typically going to do is I'm going to find which side of the stock is bowing up, and then I'm going to measure how much it's bowing up, just sweeping an indicator over it. And then I'll throw some shims under it in the center. Typically the corners will be sitting on the table, but then, you know, either here will be bowed up or it will be bowed up this way. You know, it'll have some bow to it. So I'll figure out how much bow it has and throw some shim stock under it so that when I clamp it down, I'm going to clamp it down in its bowed condition. Because one of the things, 18 watching, give this man a thumbs up. Oh, thank you, random audio guy. So what I found is if you don't do that and you clamp this down, you're going to flatten it out when you go to clamp it, and then you're going to machine it that way. And then as soon as you machine that nice flat surface, when you unclamp it, it's going to spring back, and now your nice flat machine surface is going to be bowed. So, you know, you have to try to keep the metal in its relaxed state during your work holding. So that's my thought. And then once you get the first go around done on it and you flip it over, now you have a machined, you know, flat reference spot to clamp to. So, you know, that's my, you know, 2 cents on how I'm gonna attempt to machine this and get it to come out flat. Huh, which drill holes, Josh? There's a bazillion of them. So yeah, so this part's got a lot of holes and a lot of different sizes. The tool count on this part is nuts. I think I'm up to like 13 or 14 tools. Oh, thanks, random audio guy. What are the sizes? So there's a lot of drill holes here. Most of these holes are tapped holes, and all these holes are 1032. So I've actually got most of the cam done. So all of those holes are 1032. There are a few holes that are 1024. Now I asked them, I said, you know, could you order the fasteners that are 1024 and a 1032 option? You know, try to keep everything the same. So I think what we agreed upon is that I'm just going to drill these holes out to a median size that can be tapped with either a 1032 tap or a 1024 tap, and just sacrifice some thread engagement on the 1024 tap. So those are 1024s. Then we got a whole bunch of number 6s, so these have to be tapped 632. And then we've got some clearance holes for some number 10 screws. So those are those hole sizes. And then we've got some countersinks here. So these are countersinks, I believe, for the 1024 screws. And then this bore up here, I believe, is 1 1/4 inches, and that one's 1 inch. Here, let's measure that. So this lower bore is 1 inch, and I believe this upper bore, it's 1 inch on this side, and then 1 1/4 inches on that side, 1 1/8 inches. So here's the back side of the part. So so the back side's even more fun. So the back side has this radius, you know, channel in it. So that, I believe, I'm going to have to ball mill. You know, trying to stand it up on end and do something up on end is not going to be too efficient. So that's probably going to end up getting ball milled. So yeah, the larger ones are on the outside. Yeah, these are all 1032s. So yeah, lots of holes. Yeah, you know. Yeah, Bob, that's exactly what we're talking about, is trying to hold this thing flat and, you know, getting a part this large to come out flat. You know, I'm going to try to get this flat. I'm going to attempt to get it flat within a couple of thou for them. There really is no spec, but if you missed the intro here, this groove here, this is also going to be ball milled out, is actually a bearing race. They're going to put nylon balls in it. And then its mating part is this guy here. So then this hat sits, here's the receiving balls, okay? And then this guy goes on top of this guy, okay? So this is the base plate, and then a bunch of motors and stuff mount to this. And then on this, on this guy, you notice these 4 holes and these 4 holes. That's where these guys go. So these are, I believe these are number 8s. These are 832s. So then there's 2 of these, and those will bolt to each side of this ring, and that's what makes, this thing whole. The groove in the back is a pain. Are you talking about this groove, Josh? This channel here? Or I'm sorry, Jason? A little bit of lag, not too bad. Yeah, so my plan for this groove, so this guy here, originally they did not have this groove inside here on the bottom of this bearing groove. So this was a 3/16, dish, and I think what they did originally is they just ran a 3/16 ball mill through here. But there's 2 problems with leaving this without a groove in the bottom. The first thing is that when the balls roll, if the balls are different sizes, they might just contact the bottom center here and not actually contact the edges, so there won't be any horizontal rigidity to it. It will just be vertical. So by putting this, and if you look at the design of like a ball screw or a linear bearing, they follow the exact same design where there is actually a relief in the bottom so that the ball doesn't ride on the very bottom of the grooves. It rides, on a 45 in the groove. So I added this in here for 2 reasons. One, so that the balls will, roll correctly, and then 2, it eliminates the ball mill from having to cut in the exact center of the ball mill. So it'll be a little easier to machine. But yeah, this part's going to be challenging. It's going to be real challenging. So we're going to make it, and we'll see how flat we get it, and see if it's flat enough. Again, it's a high school robot, so if it's got a little bit of warp in it, I don't think it's going to affect it operationally. It's not an aerospace part, but certainly looks like one. So if you guys have any suggestions, I know Jason said use the outside holes to bolt it down. I'm going to start, like I said, I'm going to start with toe clamps along the outside perimeter, and then some bolts in the center of it to hold it flat for the initial, machining, and then flip it over, and then toe clamp the outsides and then the inside, and then just kind of move my clamps around as I machine. So Jose would bring the material to thickness flat and parallel, and then clamp it down and machine it. So yeah, part of my other drive in my work holding is also trying to eliminate operations. So if we machine it and make it flat into thickness first, and then start with a flat, square, proper thickness piece of stock, that's one thing. If this had a really high flatness tolerance to it, I would just order the material Blanchard ground, and call it a day. But yeah, I think once it's assembled and everything, just machining it should be fine. Cost and time are very sensitive topics with parts like these. I'm not charging them any money to make these parts. And I'm trying to get the material donated for them, so I might have to end up donating some of the material. But yeah, if it had a flatness tolerance, and it was a paid-for part, Blanchard grinding the material first to get it flat and true definitely would be the way that I would go there, and then lightly clamp it to do all the rest of the machining. For the 2 medium holes, 1.25 inches. This one's inch. This one's inch on the bottom and 1 1/8 inches on the top. So, but it's a it's a pretty neat part. I like it because it's challenging. It makes you think. I don't know what this counter board here is for. Here, it's that one's 1.25 inches. That was the 1.25 inch one that I was thinking of. So there's a little counter bore there. So Jason, yeah, I thought about vise work. My big concern with putting this in a vise, so are you saying, hold it in the vise this way and, clamp here and here? My biggest concern is that by putting, pressure on the edges, you're gonna push that material up or down. It's gonna want to bow if you're clamping it on the ends. And I've held parts like this in vices before, and you don't get a lot of rigidity in the center. So if you really go at them with like a facing mill or something that has a lot of downforce, they tend to chatter really bad on you. So that's the only reason why I didn't, I don't think I'm going to go with a vise. I certainly could. I just don't know if that's going to work out. I would really like to provide clamping support, in the center here. Yeah, I'm gonna clamp it on a pre-machined piece of sacrificial material. That way I can go all the way through, the material and get all the holes in it. So my order of operations that I'm thinking here, and I just started camming it. This isn't the final cam. Is toe clamp the corners and maybe the mid, and then bolt the center down. So then it's going to be held all the way down, and then do all of this machining here first. Do all the holes. I'm actually going to poke all the holes and do all the taps first, because if I break a tap, I'd rather break it at the very beginning of the part than the very end of the part. So drill all the holes, do all the taps, do these lightning holes. This is just a 3/8 end mill going to town on these guys. Do these bores and just rough bore them, and then come back, finish bore this guy on this op, and then rough out this center, or I'm sorry, not rough out the center yet. Do this, do the bearing race, and then after all of this machining is done and the hop is all faced off, then I'm going to take this bolt out and then just rip out this center. I think that's my order of operations that I'm thinking. I thought about using some tabbing, but I only have one clamp move. So after I do all this internal machining, then I can move the clamps, and put them inside these recessed holes, and hold the material down from these IDs, and then I can go to town on machining the OD. And then once I get the OD machined, then my plan is to flip the part this way, and then I can use this straight edge as the reference to straighten the part out in X once I got it flipped. And then I was going to do my offset on this finished borehole, so that will give me a really good reference for 0. So this will get me my straightness, and then this will get me a good 0. And then pretty much on the backside machining, I got to finish bore. I'm going to finish bore this bottom ID, and then finish bore this counter bore, add these counters, add this counter, and then do this slot, and then basically just throw some chamfers on it. So that's kind of what I'm thinking of doing for an order of operations. Yeah, that's a very good point. Is to pay attention to your retract height. You can very easily knock one of your clamps off when you've got clamps in the center of a part. What I'm going to do about facing for the second side. So to face the second side, the material should be pretty darn flat already. So my plan is to clamp the outside first with some toe clamps, and then put a toe clamp right here, and then machine around the clamps. And then once I get the IDs all machined around the clamps, then flip the clamps around and clamp it from the inside. So I'm trying to only do four changes. So there'll be, you know, this will be op 10 or first op with clamps in the corners and the center. And then that will run until you get to the center piece. Then pop that center bolt out, do this center piece. Then, you know, finish chamfer everything on the inside. Then the second op would be to move the clamps to an inside location, scream out the material around the OD, and finish the size of the part. So that's op 2. Op 3 will be flip, clamp on the outside, face, you know, do all the inside operations again, and then move the clamps again to the inside, and then just finish face the outside. Yeah, Jason, I'm thinking about facing both sides first, but again, I'm trying to limit the operation. So if I face both sides, you know, first, then I'm putting the material, I'm moving the material 4 times rather than having to move the material 2 times. You know, that's the CNC side of me thinking. You know, I just try to, you know, least amount of hands-on as possible. As it is, I think this surface here, all this machining operation on this side, this is going to probably run about an hour. You know, so I'd like to be able to just put it in there and press go and come back. Yeah, Josh, I'll get right on that. Let me go up and talk to the banker upstairs and get a big surface grinder and grind it flat. That'd be a good solution, though. Yeah. There's guys in my area that have Blanchard grinders, so I could get a Blanchard ground, but I think we're going to be able to machine it flat enough to satisfy the need. But that's my general plan. You know, I appreciate the feedback and the different ideas. You know, I thought about using, you know, some of these holes, you know, for bolt hold downs and stuff, but I don't know. I don't know if, you know, using these bolt holes will be any easier, because then I'll have to, you know, pre-drill and tap hole locations in the sacrificial material underneath it. So, Harbor Freight surface grinder. I didn't know Harbor Freight made surface grinders. That would be a pretty cool trick. Yeah, I hear you, Jason, on trying to avoid the clamps for facing. Yeah, trying to use some of these countersunk holes so then the facing mill can just come right across it. I've actually gotten into trouble facing and moving clamps. So this side will be faced all with the exact same work holding, you know, so it'll be an evenly smooth face. The side that I'm worried about is this side, because this side, you know, once I get all the material gone, I won't be able to face it all in one operation with one holding setup. And that's kind of where either your comment of, you know, face the material ahead of time and get it all flat and square ahead of time before you start machining the features, or somebody else suggested do window machining and put tabs in it, and then, you know, just keep holding on to the excess stock until the part's all done and then cut it free. The problem that I ran into before is, you know, when you move clamps around on a piece this big, it's going to subtly change a little bit, and you could get some nastiness, get some nasty lips and stuff, you know, from trying to do 2 different facing operations with 2 different hold down points. I've been burned by that before. That's a good option, Josh. Yeah, I see what you're saying. Just leave the center ID intact, and then, you know, we can just bolt it here. That probably 2 bolts on this, once it's at this state, just for facing. Whoops, whoa. My rotation point changed. Having 2 bolts on here just for facing, one here and here, would probably, actually, I'm going to machine it like this. You know, one here and here for facing probably would suffice. You know, that's a good idea, because flatness tolerance, there really isn't a flatness tolerance, Easton. The flatness tolerance is basically driven by This groove is a mating groove that's going to accept some nylon ball bearings, and we want this groove to maintain pretty good flatness, just so that the top part's not going to wobble or anything as it's rotating. But there's really no flatness spec on this, not one that I've been given, but we're going to try to keep it flat. I'm going to try to keep it flat within a couple of thou. So yeah, I'm going to also explore some tabs, but here's what I've been doing for facing. So, here's the, oh, I have to unsuppress it. So this is one of the gripes that I've got with Fusion with their 2D face. Their 2D facing operation in Fusion gives you no control over, where to start, where to stop. You can't tell it, hey, there's a clamp in the way, don't hit it. You can't tell if there's a bolt in the center, don't hit it. So that's one of my big conundrums with the Fusion facing operation. So what I've actually been doing a lot with my facing is using a horizontal operation, and I've actually found that it generates a nicer looking part. So it kind of starts in the center and we do a spiral ramp down, and then it kind of spirals out and it follows the contours of the part a little bit. So then your machining marks kind of follow the contours of the part. I think it makes a nicer looking part. But now with this operation, if I clamp here, 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 and put a bolt in the center, my face mill is not going to hit it. And then with the 3D toolpaths, you can actually, specify, hey, this is a piece of fixturing, avoid this area. So I've been actually using 3D toolpaths to do my facing operations. Yeah, there's a lot of tapped holes. There's 1032, 632, 1020, and 1024 tapped holes in this thing. There's tapped holes all over it. It's a little bit too big for a mini pallet. The dimensions of the part are 14 inches across in X and then 8 inches in Y. So that's a little bit large for a mini pallet. Let me catch up on the comments here. How did I do what? Well, so Easton, this part is a pro bono part. So I'm going to try to avoid making fixturing, as much as possible. So basically the fixture is just going to be a sacrificial plate on the machine that I'm going to pre-machine flat so that I can clamp this down to it and then cut all the holes through it without machining my table. So that's the only fixturing that I envision doing. So does Fusion not have clamp avoidance? 2D toolpaths do not have any clamp avoidance at all whatsoever. The 3D toolpaths do. So, yeah, so the Pearson Work Holdings, they do the vacuum tables and stuff. So the vacuum table would be cool for this part, but I don't have one. So, I've got to work with what I've got today. So, but having a vacuum table is one of the things on my list to get, because then, yeah, the vacuum table would be pretty nice. Because if I had a vacuum table, then I could do all the same, pre-setup stuff of, measuring any bow in the plate, getting it orientated correctly so the bow is facing up, putting some shim stock under it that matches the bow, and then suck it down on a vacuum table, machine this side flat, flip it over, suck it down, machine that side flat, and then I can do Jason's suggestion and, machine both sides easily and quickly, and then you're not messing with clamps or anything, and it's pretty quick. So vacuum plate definitely would be beneficial to try to get the material initially flat, because you could do it quickly then. Yeah, I thought about doing a subplate as well, Ski, Yeah, yeah. I'm just trying not to do fixturing. You know, I've said it in a couple of my videos before. I try real hard not to do fixturing unless I have to. So yeah, I could do that as well. Um, yeah, really, the vac table won't suck it down even if you put in some heavier thickness O-rings in it. Yeah, you can do a separate sketch as well. That's one way to cam. Um, I so camming also is one of those things where everybody does it a little bit differently. I try real hard not to cam off of sketches unless I'm really backed into a corner. And the only reason being is I've gotten burned by that as well in the past where I changed some part geometry and for some reason Fusion stay did not keep the sketch linked with the part geometry. So then my tool path went all the heck, and then you end up in this forever iteration of, you know, if you modify your part. I do a lot of research and development work, a lot of prototype work. So you know, the same part gets machined quite a bit with, you know, subtle modifications to it. And if you start, you know, making a lot of sketches just to try to get tool paths to follow a sketch, you know, you're in this forever loop of trying to maintain sketches, trying to maintain the solid model, and then trying to check your cam. It just it gets really ugly quick. Oh, thank you, Shane. That's good feedback. I wasn't aware that you had that much problem with it sucking down. Are you using plate stock or are you using extruded bar stock, if I may ask? Yeah, and if there's a trace in here somewhere. Trace. Yeah, so one of these will follow a sketch path just fine. I think it's project. I think that's the one you can use this follow sketch paths pretty easily. So these other parts, I don't think these other parts are going to be quite as bad. So this is the vertical member. Again, we just got a whole bunch of drill clearance holes, tap clearance holes. This part is 12 inches, or no, 10 inches from top to bottom and 10 inches left to right at the bottom here of this curve. So this part's a little tiny bit smaller, and this one's less critical because this is just the side support. So as they bolt it together, so I believe a bolt goes here, 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 and here, and then this is supported by the plate. So as they bolt this one together, it will pull itself into the correct dimensions, um, you know, as needed. So that one's, I don't think this part's going to be too bad. And there's two of these, or there's two variants of it. So and then we've got this part. This part's pretty easy. So this part's just a vice part. This is about I think is it 2 inches, 2 1/4 by 3 1/4. So this one's not too bad. So that's a 2-op vice part. Not much to do on that one. And then these ones are a little bit interesting. I'm going to make these out of bar stock in a vise. And this is definitely going to be a windowed part. But there's really no back machining that's needed. So I can do this in one op on the front, and then just hand deburr and hand chamfer the holes on the back, you know, after I'm done. Did we lose it? Did I lose the stream, guys? Well, looks like we're okay. Yeah, I I would love to have a laser or water jet. That would be great. So T-slot edge clamps are mighty bites to flatten the sheet before using the vacuum table. Oh, okay, Shane. To initially machine it flat and then you plop it on the table, on the vacuum table. Yeah, I think we're heavily buffered. Sorry, guys. Yeah, so I got, you know, I asked permission to show all these parts ahead of time. So I have permission to film all these parts. So, you know, I'm going to do videos on making each one of these parts so you can see how I actually made it, and then I'll show you the finished product on how it actually turned out. And then, you know, everybody can, you know, try to learn a little bit more from it. Welcome, Monster. Thanks for coming and joining. I think our stream is a little bit caught up now. Yeah, I don't know if it's YouTube acting up tonight or if it's my internet connection. It's kind of weird what's going on. Thanks, Steve. Yes, they did. So I've been going through the Renishaw macros with a fine-tooth comb. Um, I'm a little bit weary on how much of their macros I can show on camera though. So I'm still figuring that part out. But yeah, so the probes are in the machine and I've been playing with them a little bit. I still got to set them up, and then I've got to start playing with them with the Fidel macros and stuff and get them going. I really wish I had them going for making these parts, because that would be very helpful. But I don't think I'm going to have the probes ready to use on these parts yet. So. Yeah, I've actually been doing a lot of customer parts, which is why you haven't seen anything get made. Um, very few parts I can actually show on YouTube from customers. Most of them are, NDA'd. Um, I've got one part for a friend that I've got to make, so I'll show that part coming up, and then I got all of these parts to make. There's a whole bunch of parts to make here, so I'll show these getting made. So. Okay, Monster. What were you confused on? I can help clarify anything if you want to ask or would like to ask. Oh, really? That's cool, Gary. What are you shooting with Seiko? So Fusion really doesn't have a way to calculate feeds and speeds at all. So I calculate all my feeds and speeds manual. I mean, here, like let me. So here's an adaptive clear. So in this example, I'm going to go all out at 7,500 RPM, and then Fusion will give you what surface feet per minute that's equated to. So that's 736 surface feet per minute. And then if you tell it a cutting rate, Fusion will tell you your feed per tooth. Um, but there's no way for Fusion to indicate tool loading or chatter, or they don't have any horsepower calculations. So there isn't a way to get a good idea of if it's going to chatter or not from within Fusion. There's a couple of good toolpath calculators out there. One is high speed machining calculator, something like that, HSM. It's not HSM Express. It's not related to the CAM software. It's another entity. And then also GWizard is a good one too. Oh, lathe grooving, Gary. Yeah, GWizard's pretty good. GWizard will actually give you an estimated tool deflection based on your cutting parameters. Um, so you can tell it what cutting parameters, what depth of cut, width of cut, what tool you're using, what material the tool is, what material you're cutting, and then GWizard will calculate a rough horsepower estimate and then also a rough tool deflection estimate. I did find that the GWizard calculator is sometimes can be very conservative. So if you have really good rigidity, it's pretty conservative. But then in other times, depending on the rigidity of your setup, it can be aggressive. So it's just a rule of thumb. You gotta get your setup going and see how it works. Um, that's what feed override pots are for. Monster, the machining tool that I used. Are you talking about my machine in general, the Fidel VMC 15, or are you talking about that little brick that I used? Here, I'm gonna. There we go. Now I'm not looking off to the side. If you guys want to talk about those parts anymore, I'll put them back up on the screen. But if anybody has any questions or you guys want to talk about the probe or something else while we're here, feel free. I've got a little bit more time left. Yes, so Fusion 360 will do ramping. Let me switch back to that. So specifically, where am I doing some ramping? There we go. So there is a helical ramp in, and then you can control that in the linking tab of almost all the tool paths. So here is your ramp control, and you can tell it what type of ramp that you want to do. You can, plunge, helix. There's some other options depending on which tool path. You can tell it the angle that you want it to ramp in and the diameter that you can that you want to ramp with. So this is in every single tool path that there is that I'm aware of. Almost all of them ramp. Thanks for stopping by, Stefan. Have a good day. Well, anybody else have any questions or anything? Yeah, I knew somebody was going to go there. Really? Um, yeah. Okay. So let me get a piece of documentation up first, and we can talk about the tool setter. Hold on one second. Let me get the manual open. Better read the manual. Imagine that. See where it calls it out. Hold on, I'm looking for it, guys. No, Steve, I've never received that error. Helical ramping too steep? Is that using one of their canned cycles? I've never received that error. I'm trying to find where the probe is, where they talk about the probe operation. Is it the macros? Oh, I know it's in here somewhere. Okay, here it is. I found it. Okay, so this is in the Fidel manuals, section 15 on touch probes. And this is page 348. So this only applies if you wire the probes in the way that Fidel expects you to wire them in. So the probe select M64 will energize one of the specific M output relays on that 1100 board that I showed. That's the one where I stuck the pins in the sockets on the raw circuit board. So M64 energizes an output, which will then set your MI8-4 to route the touch probe to the machine probe contact. There's only one input on the machine that says probe touched or not touched. So M64 will route the touch probe to the machine, or if you call an M65, it will turn that output back off, and then the MI8-4 will route the touch tool setter probe to the machine's probe input. But this only works as if your probe is installed the way Fidel expects you to install it. Then there's a second set of M codes, M66 and M67, that are used to trigger the start pulse to turn the touch probe on. So M66, when it's called, will turn on a different output, and then that sends the signal to the MI12 to send the start pulse to the optical probe to turn it on. So that's where the M codes come from, to select touch probe versus tool setter, and then to turn the optical probe on when you want to start using it. So those are the values. But again, you got to wire it the way Fidel expects you to wire it. So does that answer your questions, Bob? Yeah, so Fidel has specific macros. Well, they have specific L macros in here somewhere. Oh, where are they? Hold on, I might have to find him. Hold on 1 second. Shane, what did you add to your post processor for the warning? A specific ramp speed? Is it because the helix is too small in diameter with too high a feed rate, and it's exceeding the basically speed of the servos? Hold on, let me look for the macros. They're the L9101. So supposedly it's still in the same section for the probe subroutines internal to Fidel. Okay, so yeah, so the L9101 probe functions, and there's 10 probe functions available. Now these are the probe macros that are built into Fidel, and I don't think you have access to look at these. I never checked. We can look. So one of them is locate a touch point, center location and radius, part orientation, midpoint and angle, the Z depth. There's a tool breakage detection automated routine, computed diameter, and then there's a probe calibration, same thing that you have to go through with Renishaw. So those are the Fidel macros that are built into the machine for you. The Renshaw macros are actually separate files with separate O numbers, so they're actually programs that are written for Fidel using Fidel's macros. So that's the Renishaw stuff, and they're huge. They're like 45K, I think. I mean, it would have filled the entire machine memory if I didn't upgrade it. Thanks, Jason. Thanks for stopping by. I appreciate it. We'll make some videos on it, and then you can see how they come out. So fingers crossed. Monster, are you talking the probing functions with Fusion? So that is the one thing that I don't know. I don't know yet. I did not look into that deep yet. I was going to get the probes working by hand. But yeah, if we go back to here, they now have work touch probes set up. and you know you got to pick a probe point, and it'll just go to town. Now, what I don't know is the thing that's questioned in my mind is I think the post processor needs to support this, and you know here, let's select a probe. I'll just select a probe. Yeah, I think the post processor has to support this, and I don't think the Fusion Post does yet. So this is one thing that I gotta look at. But yeah, supposedly Fusion 360, they put the probing routines in here, so you'll be able to probe a part. Um, you know, don't know exactly how it all works yet, but that's on the list of things to crunch through. Does it work with Fidel, Gary? I thought they did. Oh yeah, it doesn't set the work offset. So what you would have to do is it's going to leave your points in the R words, and then in your program you'll have to write a little piece that would take the information from the probe and then apply it to your work offsets correctly. So I know for a fact the Renishaw macros do update your work settings, and they'll also feed back data to your tool diameter offsets. So like if you machine a bore and you probe the bore and it's a little undersized, you can feed that information back into the tool diameter offset table so that it will tweak in the tool diameter offset based on the measured part, and then you can come back and run another circle around it with the new diameter offset, and then it should bring it to size. So I was actually surprised at how thorough and complex the Renishaw macros were of allowing you that real-time feedback of going in, probing the diameter of the bore, feeding that back into the tool offset table, and then you can run a cleanup pass on it to bring it to size. So that was pretty cool. So yeah, I'm still working on debugging a new post for Fidel. I almost have it all done. I've been trying to run through all the permutations of it, which you can imagine there's a lot of. Trying to do as thorough of a job as I can of testing it. I've been a little behind the ball on that one because I've had so much other stuff pop in the way. So, but yeah, all of this stuff will be in videos at some point. I still want to make more. I thought this summer I intended to make electrical videos talking more about the electrical aspects of the machines, doing the gain and zeroing, balancing offsets, and talking about how the motor drives work and all that stuff. I just got derailed by this probe project, but that's okay because I think the probe project, a lot of people are following it and are enjoying it, so not a big deal. Like I said, somebody asked me, are you going to run out of video content? and, I said no. I probably have at least another 2 years of video content of ideas that I can make videos on. So yeah, the Renishaw macros are pretty slick. Um, they're a bit hard to follow though. I've been kind of crunching through them and understanding exactly what they're doing in there. Um, and I'm not completely understanding why they're doing some of the stuff. And I think it's going to come down to, the Renishaw macros are not necessarily written to be the most efficient macros in the world, but what they're written to be is universal. So I think the Renishaw macros can easily be modified to work on, a vast variety of different machines, and that's why they're written the way they are. But definitely not the most space conscious. If your Fidel controller only has the original 44K of memory in it, the Renishaw macros will fill up your entire memory. Here, just an idea. So the basic set of macros use up 25K roughly, and the full set of macros use up 42K. So if your machine only has 44K of memory, the advanced set of macros will use up the entire machine memory. That's a good one, Shane. You think a developer got paid by line of code? Oh, yeah, it could be. Yeah, I mean, I've been trying to sift through them. Here, I'll hold on one second. Here's my notes on the probe so far. I've been trying to figure out what all the variables are doing. So here's the list of probe variables that I've figured out so far. So what Renishaw is doing, Fidel does not have a good place to store user variables. There's a variable section, which are V callouts, but I don't know if those are retained from power cycle to power cycle. That I'm not sure on. So what they're doing is they're utilizing the top 10 tool diameter offset numbers and length offset numbers. Okay, so anytime you use the Renishaw macros, you have to be very careful that you do not use tool offset registers 90 through 99. Because if you use these, you'll overwrite the values for the Renishaw probes. So these are the permanent storage locations that they use when they run their probe macros. Then you've got these input variables, so they use the standard R variables for input, and then they use one V variable, and that's the current work offset that you're using. So then what I've been doing is kind of walking through, the probe macros, figuring out where they're, putting intermediate calculated numbers and stuff like that, and kind of seeing how their subroutines interact. Their subroutines nest, so they'll have one subroutine that calls another subroutine that calls another subroutine. So they're very abstracted, and they use a lot of variables. And there's no comments in the code whatsoever, and I think they do that just to try to save machine memory, because if you download the file into the machine with comments in it, the comments take up machine memory. So there are 0 comments in the code at all. So I've been commenting the macros just so that I understand it. I like to see how it runs, before I run it on the machine. So that's kind of what I've been up to, in the evenings when I'm trying to relax a little bit. I've been cranking at work, so I've been doing software like out the yin yang. Try writing Renishaw CMM macros. Oh, I could just imagine. Nothing else is ever in my memory. Yeah. So that's kind of my initial thought on the Renishaw macros. And like I said, I got to be careful. I don't know how much of the Renishaw macros I'll actually be able to show in a video. I don't know if I'll actually be able to show any of their code, just because it is copyrighted. The macros are copyrighted, and they do charge for them. So if I made a video and reviewing their macros line by line, you know, somebody could take that video and just retype the macros out and then get them for free. And I don't want to violate that copyright. Renishaw, is they defend their intellectual property, and rightly so. So I got to be careful on that. And then Renishaw can sell you another break-off arm. That is true as well. Yeah, we'll see how long my probe lasts. I'm trying to beat Saunders' record, because I think Saunders broke his probe the first day. So as long as I can make it through the first day, I'm good. Yeah, CMMs are nice to have, but yeah, you really have to understand how to use them and how to properly apply them. But more and more customers, you know they want you to inspect your work, and they want confidence that when you ship the customer parts, the parts are done and inspect, and they don't have to do secondary inspection on them. So having a CMM is becoming more and more a requirement if you're trying to do a mainstream shop. So yeah, and Shane, I might actually write my own macros, just because the Renishaw macros, while they are very powerful, they are very bloated. And like I said, the Fidel machine memory, they're going to fill it up. At least they're going to fill up half of it. And from what I've seen already, there's a lot of optimization that you can do. And while their macros exactly are protected, rightfully so, if I write my own macro, the math is the math. It's just taking a measurement, subtracting off a calibration factor, and then updating a work offset. So there's not really anything protected in the math. Fidel has the math, Fanuc does the math, Renshaw does the math, Zeiss does the math. So the math is pretty open, public, domain. So I can probably write a Fidel macro that will be a million times more efficient. Probably won't have the flexibility that the Renishaw macro has, but it will cover 99% of use cases. So I thought about doing that. We'll see where it goes. Yeah, Zeiss seems to be I would say, top dog in the CMM world. Most of the CMM machines that I have personally seen in the higher end shops have been Zeiss's. Yes, Jared, you are correct. I am using DNC to drip feed my programs. I am actually using a custom embedded device that I built myself. But there is a very good device out there that you can use, and it's the best $500 that, in my opinion, you'll spend. Good night, Bob. Thanks for stopping by. I appreciate it. Take care of yourself. Have a good evening. Hold on here 1 second. I'll pull it up for you so you can get the link. Okay, so this is called a CalMotion, and CalMotion is a company that first made a device that interfaces with the Fidel's controller through RS-232, and then you can either buy a USB version where you plug in a USB dongle, or you can buy an Ethernet version where you plug in an Ethernet cable, and then from your computer you can FTP to it. FTP is just a way to transfer files. It's a little bit older of a method, but it works just fine. So you can copy the files onto this extra board that you put in the machine, and then it will drip feed to the machine for you. So you don't have to have a computer in the shop. You don't have to worry about the computer crashing mid-cycle and screwing up a part or crashing the machine. So it's a standalone, what we call an embedded device, and this will allow the machine to be drip fed. And because it's just a circuit board, you can install it in the machine cabinet, so you don't have long serial lines, so you get less noise. It's just a much more robust way of doing it. It's only $500, and if I didn't go the route that I went, because I had hardware sitting on the shelf to do the exact same thing. I'm a software engineer. I'm primarily a software engineer by trade. It was easy for me to implement something that's very similar to this, and then I added a whole bunch of bells and whistles to mine just to make my workflow a little bit more seamless. So I highly recommend these. A couple of people that watch the channel I've already recommended, they've bought them, and I haven't heard anybody that is unhappy with this device. So thanks, Shane. Thanks for stopping by. We'll do another one. I'm going to be signing off here soon myself. So yeah, but there's the CalMotion. Now the other thing that I noticed recently, I don't know when they started coming out with this, but CalMotion is making this 527F CNC controller, and this one really grabbed my attention. And the reason why it grabbed my attention is because this is a plug-in replacement for the Fidel, HS88 controller. And when I mean plug-in replacement, go to their website and watch their videos. They literally pull out the original old Fidel cards, just like I did on my board swap video, and they plug new cards into the original card file. And within about 10 minutes, they've got the machine up and running using completely new controller cards, and it looks like it works awesome from the videos that they showed, and it's only $8 grand. So if you look at any other controller upgrade for a CNC machine, you're in the $30,000 to $35,000 range. So this is a huge controller for $8 grand, and it supports AC machines, DC machines. So this one really caught my attention. I would love to get my hands on one of these and review it. Yeah, you should be able to see it right at the machine. Here, I'll copy it in the chat. Hey, come on, I just want that part. Thank you. There you go. And then the specific board. This is the Ethernet version, and then there's a USB version too. here's the USB version if you like to sneaker net. I hate sneaker netting, so mine's set up as a Ethernet. So that's the CalMotion, and they've been doing some really cool stuff. So I'm pretty impressed. I actually thought about contacting them and see if I could get my hands on one of the controllers though, and you know, seeing if they would you know, promote one. Oh, the remote pendant, Gary. Yeah, I think they got the remote. I think you're right. I think they do have the remote pendants. Okay. An indexer drive for fourth axis, fourth axis indexing. Okay. Yeah, this is true, Steve. But if you're so, you know, you've got a Fidel right now. If your main processor board, you know, takes a poop, and you have to try to find a board to replace it, you know, the boards are running, you know, anywhere from a couple of $100, like $500-600 each, up to, you know, $1,000 each. So, you know, if you get a power surge or something happens to your boards and you cook your boards, you're going to pay the same amount of money to try to replace the Fidel boards with the original OEM boards today as you would pay for the CalMotion controller upgrade, and you're going to get a better controller out of it. So yeah, it's 8K, but if you think about the size of market that they're accessing, so you know they're making a controller. They made a purpose-built controller to replace an old CNC machine's controller. So their market is a very limited market. They're not making these machines anymore. Their market's not going to grow. So, you know, I think the price point that they've came out with this controller for, I believe, is very, very reasonable. And I would spend that 8K if my controller stopped working, you know, hands down. The only reason why, you know, I got another set of boards and I bought them was because you know, a viewer, you know, called me up and contacted me and said, hey, you know, there's a guy selling a set of boards, would you be interested? And I said, how much? And they gave me an absolutely awesome price. So I said, yep, ship them. That's the only reason why I got a second set of boards. It was just you know, that good of a deal. What is SneakerNet? SneakerNet is, you know, when you take your, hold on. SneakerNet's when you take your USB thumb drive and you put it in your laptop and you copy your files to it, and then you walk over to the machine with your sneakers on, and then you plug it into the side of the machine to copy your files over. I hate doing that. That's a bad workflow. You know, a lot of the big machining YouTube channels seem to be talking about workflow and all this other stuff lately. So my workflow is that I do CAM on my machine, and then I post-process directly to my NAS. So all my files are backed up on my NAS, all my customer data, everything is on my NAS, and it's on a RAID and it's backed up and all that, you know, IT garbage. And then the machine reads the same exact folders in the NAS, so I can go to the machine, I type in the job number, I got access to all the G-code files right then and there, and I can download them and stream them and be done. So that's why I like the Ethernet workflow. So Gary, the huge benefit over this CalMotion system versus the Centroid system is the Centroid system, you have to spend a fair amount of labor, you know, unwiring the whole entire machine controller, taking out the original backplane and everything, installing their controller and backplane, and wiring it all up, you know, it's a one-way street. There's no going back once you go down that path. With this, you don't have to do any of that. You literally unplug your boards, plug their boards in, plug the same cables in. There is no physical hardware changes to that machine. So what that does is that opens up somebody that is basically just a machine shop owner that doesn't have the vast background in electronics and wiring and electrical engineering. Somebody that could rewire a machine. You don't need to rewire the machine anymore. You just spend $8 grand. They ship you the boards. You follow their quick start guide. You plug the boards in. You type in your machine parameters into the new boards, and you're up and running. So that is a huge cost savings and benefit. That's what really raised my eyebrows and said, whoa, this is really cool. I'd love to try one of these out. Okay, let me catch up with the chat. Sorry, I'm kind of rambling on you guys. So how did I set up the NAS to work with the NAS? Okay. Let me bring up a website first. Oh, let's see here. Hold on one second with me here. Okay, this isn't the exact thing that I used, but you'll get an idea what I used. Okay, so for my day job, I primarily work with products made by a company called National Instruments. It's www.ni.com. They make a product line called Compact Rio. And if you watch the probe install videos, and I also did a video exactly on how I did this a while ago. I had one of these controllers at my disposal, laying around not doing anything. So I put it to work in my CNC machine. It uses a programming language called LabVIEW, which is a graphical programming language. So you can program these embedded controllers to do whatever you want. You can control industrial equipment, you can take measurements, you can do whatever you want. So it has a serial port on it. So the serial port is interfaced with the machine controller through RS-232, just like any other device would. It's got an Ethernet port on it, so the Compact Rio is on my internal network, and on that internal network is also my network attached storage. Now, as part of the driver layer for the Compact Rios, they support a protocol called WebDAV. And WebDAV is basically just a file transfer method. It's similar to FTP, but it's more secure. And my NAS internally supports WebDAV as a server. So the NAS is set up as a WebDAV server, and then the Compact Rio is a WebDAV client, and the software in the Compact Rio will go out to the NAS and then pull files off of the NAS and copy them local onto it, and then it will stream them to the machine. And then the Fidel machines, once you type in the command CD enter, that's a change device, what it will do is it will activate the RS-232 port on the machine so that anything you type on the Fidel keypad will get echoed out the serial port. So then the Compact Rio can monitor the serial port, and you can write custom commands that will only drive the Compact Rio. So you can tell it to go get a file, you can tell it to list a directory, you can tell it to copy a file, you can tell it to download a file to the machine. Then once the Compact Rio wants to take control of the machine, it can send commands to the machine just as you would type them on the keyboard, and it can control the machine remotely. So that's how the Cal Motion works, and that's how my system works in the same way of having this user interaction of monitoring the serial port for the user to type stuff in, and then taking control of the machine through the 232 port to, download files to the machine, read files off the machine, or, start a DNC session and drip feed the machine, all from, the embedded controller. So that's how I did this. I did a video on it. Let me catch up here again. I'd be very careful with a wireless serial device when you're drip feeding. If you get any pauses or corrupted data in there, it can lead to poor outcomes in the machine. So be cautious doing that. Here, hold on one second. I'll get the video link. Yeah, here it is. So here's the video specifically on that system of, interfacing the machine to the NAS. I think I actually reviewed the code in that video too that I used. So, well, we're rolling up on midnight here, so I think I'm going to wrap this stream up. Anybody else have any last minute questions? I didn't even look to see how many people we got watching. Still, I know we had like 20 at some point. Wow, 12 people still here. Cool. I think we built up quite the delay with my internet problems. The stream dropped out there for a little bit halfway through, so. Oh, you're welcome, Seth. Thanks for watching and hanging out. Appreciate it. Oh, you're welcome, Jared. Thanks for coming. Dynapath. Wow. Do you know what year that was made, Gary? In 1984. So, well, at least I was in school at that year. Thanks, Steve. Thanks for coming. I don't know what I'm going to do the next one. Like I said, I've been pretty hammered, and we got to get all these parts machined for the kids. So, it might be another couple of weeks before I do another one. But yeah, we'll try to get more of these in. So, okay, folks. Well, for those of you that stuck around, thanks for watching. I greatly appreciate it. And, if you have any questions, feel free to email me or drop some comments. And we'll see you on the next stream. Have a good evening.